Oh, you want to play it now? Okay, so this is what we have learned. Fit of some number and analyze the effect of number on the fluid flow. Then we have all these equations. In the tutorial, we use it a lot. Okay, you don't need to remember this one, right? This one is just simply you put my number as 1, you will get the critical condition. Okay, this critical condition is different with the critical condition in your thermodynamics. Okay, in fluid mechanics, especially in the compressible flow, the critical condition is occur only at the throat when the Mach number is equal to 1. And you can only get Mach number equal to 1 at the throat when there is a critical condition, right? The critical condition is where the pressure is the minimum, right? You cannot have it lower than that. Okay, and this is what we have learned last time. If you have converging nozzle, right? If your inlet and outlet has the same pressure, there will be no flow. When you reduce it, then there will be some flow coming on, right? This is the pressure distribution within the converging nozzle. You know, the smaller the area, the higher the velocity. The higher velocity, the lower the pressure. It's as simple as that. That's why you can see the pressure is going down. When you reduce it further, it will reach the so-called critical condition. Okay, in this critical condition, the Mach number at the throat will be 1. Doesn't matter whether you reduce it further, the exit temperature will be the critical pressure. Right? So that is the lowest pressure you can achieve at the exit of the converging nozzle. So you can see the exit pressure is equal to back pressure when EB is more than P star. Right? But when EB is less than P star, doesn't matter what your exit temperature the exit pressure, the pressure at the exit plane will be equal to P star. You remember that? Okay, so this is the thing that you need to remember for the converging nozzle. But then, how about one more thing is that when you are reaching the critical condition, your mass flow rate will be maximum mass flow rate, right? So if you have reached the maximum mass flow rate, the only thing that can change your mass flow rate is the stagnation condition and the area. So you can see that. So if you increase the stagnation pressure or decrease the stagnation temperature, you will get a higher mass flow rate. When you do the reverse, you decrease the stagnation pressure and increase the stagnation temperature, you will decrease the maximum mass flow rate. Okay, so that's about the isentropic flow through the nozzle. So this is what you will get. Okay. If you come to the tutorial, I know most of you are missing the tutorial, right? I know that. Anyway, that's okay. So you can see that this table and that thing will give you the same value when K is equal to 1.4. So this table only applicable for K 1.4. What happens if my K is 1.667 or 1.3 or 1.47 or 1 point something different? You cannot use this one anyway, right? This one will not be applicable. But sir, I'm so desperate during the test, I will use it. It's up to you. Right? So if you want to do that, if you want to get this table for different K, you can open your Excel, right? Your Excel, and then put this equation to that, and then you will get another set of table for that particular K. But unfortunately, you will not be able to bring that, right? So better use this one. Okay, and if you remember in one of the tutorial, question number 4, you get the value in between 2.6 and 2.8, right? 2.6 and 2.8. By right, you will think that, okay, I have the table, I have the K is equal to 1.4, why not I do the interpolation? Okay, you can do the interpolation, but remember when you do the interpolation, you do it linearly. Right? You do a linear interpolation, but you see the equation? It is not linear at all. So So the result will be totally different. Okay, so unless you get it exactly, like if you have 2.6, you can use it. But if you have 2.68, like the one in our tutorial, you better not use it, right? Because the result will be quite different. Okay? Any question about that? So this one will only be applicable if you got K 1.4 and exactly as is. If it is very close, let's say you have 2.398, then it's okay, then you can use 2.4. Right? But if it is 2.4 or 2.5, you will be in trouble.
Can we interpolate?
Yeah, I told you can do interpolation, but your interpolation will be linear interpolation. But the equation is not linear. Okay, the result will be different. Will it totally wrong? No, of course it will not be totally wrong, but you will not get the full mark. Right? Because it is not correct. Okay, so this thing is applicable not only for a converging nozzle, it is also applicable for converging and diverging nozzle. That's why you can see, right, the A over A star is growing smaller, right? It's reducing and then it's increasing. So at the ratio of 1, you can see when A is equal to A star, which means this is the condition at the throat. When you reach the condition at the throat, Mach number will be 1 and everything will be given here, right? Okay, and this is, we have gone through this question. Okay, you remember. Okay, one more thing. If you are given the equation for the compressible flow, the pressure over here is the absolute pressure. Right? That's why you can calculate the rho easily by having P over R, sorry, PRT. Right? Rho is P over RT. And then you can use those P right away. Because those pressure is the atmosphere, or the absolute pressure. It is the total of gauge pressure plus the atmospheric pressure. So when you have this kind of question, those P is the SI, the absolute pressure. Right? Remember that. That's why you can use this like this thing directly. Okay? So those thing is not the gauge pressure. That's why in the case of this problem example, you can see this problem example, you need to change the P, because this one is gauge, into the absolute pressure. Okay? When you are dealing with the compressible flow, always use absolute pressure. Because ideal gas only working with absolute pressure and absolute temperature. Right? You cannot use degrees Celsius, you need to use Kelvin. Okay, you need to use Kelvin. And remember all the units, that's why I keep all the units with me. You see this one kilopascal, this one kilojoule. If you are not careful with this tool, you may not get this one. It will be totally different story. Right? Because rather than 0.287, it has to be 287 joule kilogram Kelvin. Remember that. Okay? You may remember today, maybe not the next time. Right? I'm really happy with that.